Right. So say you wanted to calculate the determinant. So remember with the 2 by 2, we calculated the determinant, and then we had a little formula for finding the inverse. And there's you can do the same thing for 3 by 3 and beyond. But here's just what the determinant looks like to calculate. You may have done this last year. You used Cramer's rule as a solving method for a system of 3 by 3 equations. You've done this before. But here's what it looks like. And here's the process you go through. You take and identify the top left number, write it down, A, that's a coefficient. You cross out column and row that A is in, and what's left over, you have to then calculate that 2 by 2 determinant. So you have to know how to calculate a 2 by 2 determinant to be able to get the 3 by 3. And then, of course, to do a 4 by 4, it would be the same process. But so you picture what row and column, you'd have a 3 by 3 left over, then you deal with that. So it's one inside of another inside of another. Oh, okay. But obviously it's not difficult to code it into. I mean, your calculator can do this. Your calculator can calculate the determinant for 4 by 4, 3 by 3, whatever, 2 by 2. So it's not difficult. And then the signs alternate. So the next one would be minus, and you would move down this column. No. There's 3 terms here. You'd move down the column to B. You cross out row and column of B, so you'd write down B, and then you have the determinant of R, X, T, Z. And then alternate sign again, plus, and then guess what the next one is? C. So very pattern-based. You could do it. We just don't want to do it, right? Me neither. So C, and then it'd be the determinant of R, X, S, Y. And then, of course, this is A times, in parentheses, now this we should know. Determinant of a 2 by 2 is not hard. Just SZ minus TY, and then minus B times RZ minus TX, and then plus C times RY minus SX. Okay, so here's what we're doing. Well, I'm not going to require you to. I may not even have you do this again. Your calculator can calculate it for you. So I just wanted to show you that you can, by hand, okay, with this it's kind of a built-in process. If you know the 2 by 2 determinant, how to calculate that, you can calculate a 3 by 3. If you know how to do a 3 by 3, you could do a 4 by 4 and so on. This would only be useful if you had to do some programming. But what I'm doing is I'm taking each of the elements of the first column, circling it. You can see with C, circle it, cross out column and row, and then the determinant that's left over, do you see the determinant that's left over? Is a 2 by 2, and I'm calculating that determinant. So, could we calculate the determinant of this 3 by 3 with this formula? Sure. What would go first? 4, right. And what 2 by 2 determinant would be left over when I cross out the row and column that 4 is? 3, 4, 8, 1. And then what do we have to remember about the sign? It's negative. And then what's the next term? Moving down the column. Yeah, but we'll just write it out as negative, negative 9. And then the determinant that's left over, when I cross out the row and column that negative 9 is in? 1, 0, 8, 1, yeah. And then plus negative 3. And then the determinant left over is 1, 0. Yep. Positive, negative, positive. So 3, 4. And then we could calculate the value. So a determinant, what is a determinant ultimately? It is. It has many uses, but it's just a number. A determinant is a number. It's used in figuring out what the inverse is, or it's used as a. It is when you're using Cramer's rule. or when you're using it to find the inverse. Yeah. But it's just a number. That's all a determinant is. It's just a number. And it can be used in theory to decide if a matrix is invertible in the first place, if it has an inverse. So here I have 4 times 3 minus 32. And then this is plus 9 times 1 minus 0. And then this is minus 3 times 4 minus 0. So it all comes out to equal, I think, negative 119. You want to see how to do it on the calculator? Yes? So negative 119. Let's see if we can get that same value on the calculator. Does anybody else want a calculator to borrow?
Yeah, Mr. Brown's there.
That's it, all got it.
I don't want to.
Sorry. The best way to learn how to do this is to learn it by doing, though. But sorry. Oh, I do have one more. You can borrow mine. Okay, I'm sponsored by Texas Instruments. So let's go ahead and do it on the calculator here. So I'm going to have to grab my notes so I can see what I'm typing in. All right. So on the calculator, you go to second, and then the x inverse key. That's our matrix. Go over to edit, and I'm just going to select number 1. If your matrix is not a 3 by 3, you need to type in 3 by 3, and then it will change to that size. And then we just type in the values in the rows. So it goes 4, 1, 0. And the second row is negative 9, 3, 4. And then the next row is negative 3, and 8, and 1. Does anybody need help entering in the matrix? Did you get it? All right, and then if you go to second in the x inverse key, unless you have the TI-83, there's a matrix key somewhere over here around where programming. And then go to math. So this is all the math you can do with matrices. Okay, well, or a lot of them. And the very first one up there, look at that, must be important, is determinant. The next one is, that's a symbol for transpose. Next one's dimensions, fill. So just select determinant. I think what I need to do though is, I don't know if I've quit out of the menu. So make sure you have a blank screen. Second quit, maybe hit a second quit, and then go to second x inverse, go to math, determinant, and then you just type in, well, you have to select the matrix that you want to find the determinant of. So you go to second matrix again, and then under names, just select number 1, and then finish your parentheses, and then hit enter, and there's our negative 119. So, yeah, I mean, you can use this to find the determinant. Well, if I ask you to find the inverse of a 2 by 2, you could just have a calculator do that for you as well. So, you know, what's the point? What's the power of matrix algebra? Well, we're forgetting it. Look at number 2. We have a matrix equation. We have AX equals B, and I left some space over there because if I want to get X by itself, the X matrix by itself, I have to multiply on the left by A inverse. Do you remember that? Our equation, our generic equation here is AX equals B, and what I want to do is X equals A inverse B. So what I need to do is have the calculator, I haven't shown you how to do this by hand, we're not going to do this by hand, but have the calculator find the inverse of this matrix A. We're going to put a little inverse sign by it. and multiply it by b. So, we could have the calculator find the inverse and then write a matrix without the little -1 sign on here. We could actually write what the inverse is. We can also have the calculator calculate the inverse of this for us. So what we're going to do, that's actually what we're going to do, is we are going to go back to our calculator here, and we're going to enter in that matrix A, and then have the calculator find the inverse of it and multiply it by B, all in the same step. So on your calculator, go to second x inverse, go over to edit matrix A. We're going to change matrix A up. The dimensions are already correct, so you'll have to arrow down twice to the first row. And then I'm going to enter in 2, 6, 6. That's the first row of that matrix A. 2, 7, 6. That's the second row. And then the third row is 2, 7, 7. Don't forget to hit enter after that last entry. And so just double check, maybe make sure the matrix is in there correctly. Like doing construction, measure twice, cut once. So check maybe, otherwise it's going to cause you a grief here. So there's my matrix A. I need to go back to the matrix menu and edit matrix B as well. So go over to edit. Hit number 2, matrix B, you'll have to make it a 3 by 1 if it's not already. And then we're going to enter in 8, -7, and 1. So 8, -7, and 1, just double checking it. Oh, okay, that's why we double checked. 8, yeah, I was already down to the next one. 8, 10, and 9. So try it. 8, 10, and 9. 8, 10, and 9. And I told you what the inverse was, just with the thought that you could then pop that matrix in there and multiply it by hand if you wanted. But we're not going to do this multiplication by hand with the 3 by 3. So quit out of here. Then we just type in the matrix equation. So you go to second x inverse, pull up matrix A, and we want matrix A inverse. So you hit the x inverse key, and then I would not have even needed to give you that inverse matrix. It will calculate it for you. And then go to second x inverse, hit number 2, and that matrix equation A inverse B, you can use that over and over and over again and just change the matrices, and it will solve 3 by 3 for you. So hit enter, and what is this telling me? Yeah, that's it. X is 1, y is 2, z is -1. So you'd have a triple, an ordered triple, if you will. So this x is, it was 1, I forgot already. 1, 2, and -1. Okay. And when I say x, that's a capital X, which is representing a matrix. And so, the ordered triple, or the solution, is 1, 2, -1. Okay, that's the ordered triple, if you will. But you can leave it in matrix form. This was just a matrix equation. I'm not trying to connect it to any type of system of equation. So we're going to skip over number 3 here. Number 3 is just doing the same thing. Like I said, all you would have to do is change matrix A and B, and then reuse that equation, A inverse B, and it will solve. So what's the point of all this? What's the point of all this? Down on number 4 here. We've got a system of linear equations. Last year you learned how to solve one of these. It sounds like with 2 methods, probably using elimination combined with substitution, as well as Cramer's rule. Those are 2 good methods for finding a solution to a system of 3 equations with 3 unknowns. So don't write this down. I just want to show you the process that you would probably have gone through. Okay? Let's talk through it, just to review. What variable would you eliminate first, do you think, on these equations? What would you guys eliminate first? Okay, you could eliminate x from the first 2, you mean? Yeah, you could do that. You could also eliminate z from the first two. Why did you switch to z? There's no z for the third, so then you'd be ready to go. It's not, we get somewhat messy numbers, but it's not bad. If you wanted to eliminate, I'll just draw a little arrow over here. If you wanted to eliminate z from the first two equations, what would you multiply the first one by? 5. Okay, the least common multiple is 30, so 5 and negative 6 would be the plan. Good. So my new equation would be 20x minus 25y minus 30z equals negative 5. You don't need to write this down. You've done this before. I think you could do it again. It's a good review, though. And then we have negative 6x plus 12y plus 30z equals 72. You'd put a line underneath it, you'd add them, and your new equation would be 14x minus 13y equals 67, right? Okay. So this equation, now, you could bring this other one underneath it, 2x minus y equals 7. Now it's like, you know, an Algebra 1 problem. And we won't do the rest of it, but I just wanted you to see how much work is involved with solving a system of linear equations using elimination. Okay? Because this will help you to appreciate matrix algebra. Well, there's technology that'll do this for you, yeah. And this is what I'm encouraging you to do as you move on to the calculus. You have all these methods at your disposal. Why not use matrix algebra when you're asked to find the solution to a system of 3 equations with 3 unknowns? Yeah.
You just showed us that so we can appreciate the calculator.
Correct.
Okay.
I'm not done yet either, but this goes back to Algebra 1. I mean, this would be a hard Algebra 1 one because of the least common multiple, and, well, it's a 13. You could eliminate the y maybe. But anyways, you could do this. You've done this in each of the courses leading up to this, right, since Algebra 1. So there's a lot of work, and you'd have to go back, substitute to get x, y, and z. It's a lot of work. But with matrix algebra, it's not that bad. Let's do this with matrix algebra. What would I enter in for matrix A here? So looking at your notes, and have your calculator ready, what would I enter in for matrix A? Let's go to second x inverse. We're going to go edit matrix A. And it is a 3 by 3, although we're going to have to fill in a blank there. There's a little blank, we'll have to take care of that. But what would matrix A look like? We have across the top 4, yep, just the coefficients of x, y, and z. 4, negative 5, and negative 6. The next one would be 1, negative 2, and negative 5, and this next row has a bit of a hitch in it, but I think you'll handle it fine. 2, yeah, negative 1, and then put a 0 in there, yeah. Represent that coefficient of z. So we type it in. And as long as you can find the inverse of a matrix, this is the way you want to solve 3 by 3s and beyond from here on out in your math. Okay. Second quit. Go to second matrix, number 2. Matrix, this is the answer column matrix, and it will be negative 1, and then negative 12, and then the last term is 7. So we have our 2 matrices, matrix A and B. And let the calculator figure out the inverse of A and then multiply it by B for us. You got that entered in? And now, if you calculated the inverse of A separately, it's a bit of a mess. It comes out with decimal approximations and so forth. But we are going to not even be able, we're not even going to worry about any of that. So quit out of here. See that equation A inverse B? I can hit second, enter, it will recall that equation. So if you hit second, enter, it will recall the previous line, A inverse B. I have already changed A to B. So I just hit enter, and there's the solution.
Oh, myself.
2, negative 3, 4. I have to show you this. If I were to calculate A inverse by hand, here's what A inverse looks like. Here's A inverse, just so you can see it. There's A inverse. So, now, those are rational numbers. Did you know that? Can you tell, like 0.4166, you see that right there? When you have a repeating or a terminating decimal, it's a rational number. Math, fraction. And there they are. Isn't that cool? But so the calculator will take those decimals that it popped out and then actually change them to fractions. So here it is, a fraction for it. That's A inverse. Can you imagine calculating that by hand and then multiplying it by B?
Math.
But it's programmed into your calculator, your little handheld calculator. So this is the way we want to solve a 3 by 3. Now, if there was not a solution, or if there were infinitely many solutions, remember those other two cases? No solution or infinitely many? It will give you an error message. It'll say dimension mismatch. It'll give you an error message. It's just telling you it's one of those other two cases. There's not a unique solution. And then you have to deal with it with other methods. Okay? But if there is a unique solution, this is the way to go. Any questions on that? And I'm going to have you do this on your quiz and on your test with the calculator. I just want you to know how to use the technology to solve A inverse B. Yeah.
So this is the end of the packet. Is there more?
Now this is the end of the packet. This is it.
Our test is on Thursday.
And the quiz is on Thursday, and then we're going to do a little more reviewing. We have that week in between, and we'll do the test at the end of next week.
What are you doing next?
The what? Yeah, let's go to the next page. All right, this is called Gauss-Jordan elimination. Let me preface this just a little bit. This is a method of doing elimination, doing what you did last year with elimination, but doing it in matrix form. It's something that if you go on to linear algebra, you'll talk a little bit more about Gauss-Jordan elimination. As a matter of fact, guys, if we had gotten an error message when we tried to do that, in other words, if say one equation was a multiple of another, in other words, we couldn't get an x comma y comma z that's unique, we would have to go through this process or elimination to figure out what the dependence relationship is. What I mean by dependence relationship is that, for example, z might depend on what x and y are. So z might just be an equation rather than a specific number. Okay? And the only way you would figure that out is if you were to go through this process of Gauss-Jordan elimination, which is really what you were doing when you did elimination last year. Okay? Here's the goal with Gauss-Jordan elimination, and we can shorten it up just a bit. But the goal is to use elimination techniques. What I mean by elimination techniques is multiplying one equation through by one number, another equation through by another, and then adding them together, right? Those are elimination techniques. Until you get to a point at which you have all ones on the diagonals, and at a very minimum, all zeros to the left of the main diagonal. Ultimately, if you wanted to solve for x, y, and z and get your a, b, and c, or whatever those numbers are, you'd have to have zeros here. But we can stop once we have zeros to the left of the main diagonal. Here's why. When I have a 0 here, this is the coefficient of which variable? Not z, x. Okay, it goes something x plus something y plus something z equals something. This is called an augmented matrix, by the way. It's a 3 by 3 matrix with the answer matrix attached to it, just to keep track of it. It's just another way of writing this system of equations in shorthand, okay? So the coefficient of x is 0, the coefficient of y is 0. So this tells me, what's the coefficient of z? 1, right? So this tells me Z equals C. So when I get my matrix down to this point, I have solved for Z. When I get my matrix down to this point, I have solved for Y as well. Y equals B. And I've also solved for X. X equals A. Now, Gauss-Jordan elimination is simply, and I'm going to demonstrate this to you, but in terms of, it's more theory, I'm not asking you to memorize or do anything. I'm going to just show you what it looks like. It's a shorthand method for doing elimination is all it really is. Okay. And it takes a little bit of practice to do it. I'll show you an example here, let you try it. But the big picture is, can you solve a solution, a system of 3x3 system of equations using matrix algebra is what we're getting at. And the point of this is that we would use Gauss-Jordan elimination if for some reason we did not get a unique solution using A inverse B. Okay. So here I have this system of 3 equations and 3 unknowns. I'm going to write this in an augmented matrix form. So this would be an augmented matrix form: 1, 2, 3, dashed line 0, -1, 3, 2, 0, and then -2, -3, -2, and 3. So here's what my goal is on this. And we're just going to take it to the point at which we get zeros. We want zeros here, here, and then here. And then we can take it from there. We don't need to get zeros up here. Once we have zeros here, here, and here, it's going to be a one-step equation to solve for Z. And once I know Z, I can substitute in to this equation that will be left here to get Y, and then I can substitute Z and Y into this equation to get X. Okay, that's the idea. And so think about what you would do with elimination. Say, for example, I want to get rid of one of these numbers here. Say I'd like to get a 0 right here in this middle left, second row, far left side. What would I have to do with these 2 equations? And maybe it's easier here to get a 0 here. It's ready for elimination, right? What would you do with these 2 to get a 0 right here? Add them, yeah. If you added these 2, you'll have a 0 right here. You're just taking what's called a linear combination of the 2. And so what we do is we write a little recipe here. We're going to tell ourselves, we're going to take row 1 plus row 2. And that's going to give us a new augmented matrix. Now, the trick is we don't change. One other thing I like to do here, another thing I think that'll help you, is I write the little recipe corresponding to the row I'm actually going to change. So I'm writing row 1 plus row 2. It's only going to change the middle row here. The other 2 don't change them. In other words, row 1 will remain 1, 2, 3, 0. And row 3 will remain -2, -3, -2, and 3. But row 2 will change. Row 2 is going to be what we call a linear combination of row 1 and row 2. And Gauss-Jordan elimination is saying, okay, all that you're doing is you are rewriting this in such a way that you have an equivalent equation. I mean, you're going to have the same solution, but you've changed one of the 3 equations. It's like what you do when you multiply through by a constant here. You still have the same equation with the same solution. It's just a linear combination of that original equation. So let's add these 2 and write our new row here. So this -1 plus 1 plus -1 is 0. 2 plus 3 is 5. 3 plus 2 is 5, and 0 plus 0 is 0. So that's the only thing that changed, was that middle row. But I accomplished getting a 0 right here. my goal is to get zeros here and here as well. So do you have any ideas on how we could get a 0 in the bottom left right here? What would I have to do to this equation before adding it to this equation to get a 0 here? Double it. So here's what the recipe looks like. We're going to take, let's do this. Now, what's the row that's going to change? Only the bottom row. So I'm going to write the recipe corresponding to the bottom row, and the other two rows are going to stay exactly the same as they were, okay, in the previous matrix. So I'm going to write down 1, 2, 3, dash, 0, and then 0, 5, 5, 0. Those are going to stay the same. Don't change them. And my recipe is going to say take 2 times row 1 and add it to row 3 and tell me what the new row is. So think you can do that in your head? So we're going to take 2 times row 1. So 2 times row 1, that'd be 2, and add -2 to it. And I have 0 here. Then go 2 times row 1, so that'd be 4, plus -3 is 1. And then 2 times 3 is 6, plus -2 is 4. And then 2 times 0 is 0. 0 plus 3 is 3. That's my new row. All right. We're almost ready to solve this thing. So really, guys, this is just a shorthand for what you've done before. We're writing it in augmented matrix form, but all we're doing is elimination. Just doing elimination. I want a 0 right here. I want a 0 right here. Any ideas on what I could do to get a 0 right here? I could, but then when I add it to the top one, I'm going to reintroduce a number here. And that's not going to be helpful. So I started with a 0 here, and then I got a 0 here, and I did that for a reason. I would like to work with just the second and third equation. Because if I bring the first equation back into the mix, I'm going to introduce a number back here, which is okay. But that's going to be a little counterproductive. There's nothing wrong with it, but it's not going to help me in getting my zeros here, here, and here. Okay, so what I want to do is combine these two, but what do I need to multiply this by? -5, right. So, okay, what's not going to change? Okay, which rows are not going to change? 1 and 2. So let's copy them down. It's one of those things, if you take a linear algebra class, you'll talk a lot about this. You'll talk more about the theory, what's behind it. But the only reason I'm showing this to you is because this is what you would have to do if A inverse B did not give you a unique solution. You would need to do this to get your dependence relationship, or ultimately go back to elimination that you learned last year. You could do that too. So right here, I'm going to take 5 times, I'm going to do 5 times row 3, actually -5 times row 3, right? And then add to that row 2. So let's do that. So we'd go -5 times row 3 is that 0, and then add 0 to it. That's good. We want that to stay 0. -5 plus 5 is 0. Oh, that's good. That's what we wanted. -5 times 4. Almost went times the wrong. -5 times row 3, and -20 plus 5 is 15, and then -5 times 3 is -15 plus 0. Did I miss it? -5, -15 plus 0. Yep. Is it negative? So -5 times 4 is -20 plus 5, negative 15. You're right. And actually, your calculator will do this as well. It'll do this row by row on a matrix and reduce it down. All right. So what does this mean? We can stop right there. Believe it or not. What does this mean? What does z equal? Okay, this right here means negative 15z equals negative 15. So z equals 1. Box it. Right. Z equals 1. What does this mean right here? 5y plus 5z equals 0. So what is z? 5y plus 5 times 1 equals 0. Solve that for y. You get y equals negative 1. That's what I'm hearing. Okay, good. And what does this mean right here? X plus 2y plus 3z equals 0. Put a little bar there. And I know z and I know y, so it's x plus 2 times negative 1 plus 3 times positive 1 equals 0. So x minus 2 plus 3 is 1. X plus 1 equals 0. X equals negative 1. And I have my solution. And it happens to be a unique one. And there's all kinds of stuff behind it. Like what'll happen if you have a dependence relationship is you'll get all zeros down here. Like the z will drop out. So you might have something like z is dependent upon what x and y are and things like that. But that's Gauss-Jordan elimination. It's just really a shorthand for the elimination you've done before. All right. Just want to show you one applied problem here. It says use a calculator to find that REF, that's row reduced form. We're not going to do that. We'll just use matrix algebra to solve this. Could you write an equation for this word problem? It says tickets to the play are $2 for children, $3 for teens, and $5 for adults. The show grossed $1,950 and 570 tickets were sold. Yeah. 3/4 as many teens as children attended. How many of each ticket category were sold? Can we get 3 equations out of this, you think? Take the first sentence, right? Let's let C be children, T be teens, and A be adults. We have 2C plus 3T plus 5A equals, how many tickets were sold? Let's see, this is the dollar amount, so $19.50. $19.50 goes here on the right because the 2, 3, and 5 are all dollar amounts. So this is our dollars equation. Okay. When you did systems of equations, you always had a dollars equation and then just a total amount equation. My total amount equation would be the following. I know that child tickets plus teen tickets plus adult tickets has to equal 570, right? That's just my total equation. And if I have 3 letters, I need 3 equations to solve this using matrix algebra. So that last sentence on there says 3/4 as many teens as children attended. So 3/4 as many teens as children attended. So we could say, okay, 3/4. Let's see here. That doesn't say anything about the adults. So 3/4 C. Well, let's do it this way here. We have 3/4 C equals T. So if I were to write an equation for that, we would have move the T over. 3/4 C minus T equals 0. That's the relationship there. 3/4 C equals T. So 3/4 C minus T plus 0A, if you will, equals 0. If I have, this is my equation right here. The relationship is that 3/4 of C equals T. So if I subtract the t over, this is my equation, 3/4 c minus t equals 0, which has a coefficient of 0 for the adults. So this would be my equation. You think you could solve this using A inverse B? Once you set it up, you sure could. Okay, sure could. So this is one application of that. I'm going to leave it at that. That's the setup for it. Let you solve it on your own. Let me pass out the worksheet here. So, too many problems on here. Maybe leave your calculators there. Put your calculators are ready to go. Yep. See if you can find, if you have time here before the bell rings. You'll have to do it on your own time.